This equation describes the dissociation of water vapor into hydrogen and oxygen gases. We can write an equilibrium equation for this. Look up to the upper right, you see concentration of O2 to the 1/2 power. 1/2 power means square root. And then if we go and get the equilibrium constant for this, we have 10 to the minus 41st at 25 degrees Celsius. And we want to see what kind of information we can get just from looking at the numerical value of the equilibrium constant. 10 to the minus 41. That's a really small number. Look up above there at the equation. If you have a really small number, what's bigger, the numerator or the denominator? Now, I know you can look at it which one's smaller, but I have a reason for approaching it this way. For a really, really small number, that means the denominator is much bigger than the numerator. And the denominator corresponds to the reactants. Here's a methanation reaction that involves carbon monoxide and hydrogen gases, which makes methane and water vapor. We can write an equation for that. And then I go and get the equilibrium constant. At 25 degrees Celsius, it's 10 to the 27th. Same question I asked before. 10 to the 27th. What's bigger in the equilibrium equation, the numerator or the denominator? Well, the numerator's a lot bigger. And the numerator is where we find the products. This reaction describes the formation of ammonia from nitrogen and hydrogen gases. If you have something to the 3/2 power, like we do for the concentration of H2, you take the square root of it and then you cube it. The numerical value for that at 25 degrees Celsius is 747. What do these three values tell us? What do these three values tell us? Well, the top one, that was 10 to the minus 41st. And that was a really small number. Okay, so from a really small number, what we can get from it is that at equilibrium, it's mainly reactants. In other words, the reaction doesn't progress very far at all. If we have an equilibrium constant that has a very large number, well, that corresponds to products. So that reaction progresses pretty much to completion. We end up with almost all products at equilibrium. And then this third case, 747. Well, it's not a really big number. It's also not a really small number. And the best we can get from that is at equilibrium, we have appreciable amounts of all the reactants and all of the products. Now, different books have different guidelines on this. One that I've seen is that if your equilibrium constant is greater than 1,000, then it suggests that it's mainly products. If it's less than 1,000th, that means it's primarily reactants. And if it's in between those two, it's a little bit of everything. Other books, 100 to 100th. I'm not out, at least in my classes, to trick anybody. So I would think of it this way. Stupidly small number. Primarily reactants at equilibrium. Stupidly large number. primarily products at equilibrium. A value that's not real big or real small, appreciable amounts of everything at equilibrium. Now that third case, with the Kc of 747, we're going to learn how to do calculations, and that's primarily where we're going to live, is in those reasonable values of the equilibrium constant. In other words, nothing too large or too small.